Hello everyone and welcome to this course on modern application development. So now comes the question of efficiency. Let's look at that, right? First question, what is the most common language on the web, right? And the fact of the matter is, whether we like it or not, probably just in terms of the volume, the number of web pages that are there, English is the most common language, at least now. It might be replaced by Chinese or maybe some other Indian language or something else, right? But it is the most common language, and not only that, given the fact that many of the European languages use the same script, a large part of even the non-English language web would use the same set of characters, or at least mostly the same set of characters. So it made sense to sort of go with ASCII for a long time. But then comes the question, obviously you have other languages, you want to be able to represent them. When we start adding things on, and as we saw that UCS 4 is good enough, right, 4 bytes per character is good, but I don't want to be storing 2 kilobytes when I have only 500 characters worth of information, right? So let's take an example. Supposing I had a text document with 1000 words, right? Now this would be approximately 5000 characters if we include spaces, right? Depends on what a word means, right? So I'm going to assume 5000 characters as the size of my text document, right? Now with the UCS 4 encoding, right, 4 bytes per character, that's 32 bits per character, I end up with 160 kilobits as the size of this document, right? Is that acceptable? It depends on the context, but let's see if we can do better. With the ASCII encoding, right, that would have come down by a factor of 4. So clearly UCS 4 is not particularly efficient. It might allow you to do a lot of stuff, but if I know that my document is in English, right, do I really need to be spending this much space, right? Because ultimately this needs to get stored somewhere on disk, in memory, right, and it needs to get manipulated, which means that I need to load 4 bytes every time I need to get one character of a string. Comparing strings becomes more difficult, right? It has many impacts that we can't just ignore. So with the ASCII encoding, it would have been much better, only 1/4, 40,000 bits. The original 7-bit ASCII, which would be enough if it was an English document, would be only 35,000 bits, right? An additional sort of 8% improvement if you really look at it. But the minimum that is required if we just want to encode A to Z, small letters, forget capital letters, numbers and maybe a few special characters, right? You could fit it within 6 bits, that would bring it down to 30,000. Right? This is sort of artificial because I clearly would want some kind of capital letters and so on, right? But okay, at least as a thought experiment, it's useful. Now, even more efficient encodings are possible, right? Because from your reading of any documents in English, you would have noticed that certain letters occur more frequently than others, right? So Z and Q, for example, are fairly rare occurrences in regular usage. E, on the other hand, is the most common, right? And this is pretty much well known from a analysis of a large corpus of English language documents, right? The sequence of the highest frequency letters, E is the most, then T, then A, and so on, okay? And Z, Q, J, they are at the bottom of the list, right? For those of you who play Scrabble, you would have noticed that the points for Z and Q and J are correspondingly higher, right? And they are also rare. So there are encodings such as, for example, the Huffman encoding, which would allow you to spend fewer bits on something like E and more bits for something like Z, because I know that E will occur more often, and if I can represent it with fewer bits, net I will get a saving, right? And I might even be able to get by with something like 10 to 20,000 bits for this document that I have. Is this the least that I can do? That's not a good question to ask, because now it starts to depend on the document. Supposing this document that I've said has 1000 words basically had one word, right? And in fact, if that word was just A, right, space, repeated 1000 times, I could just come up with a very nice encoding which says, take this particular letter A and have one thing which says X 1000, right, repeats 1000 times. So that would be a total of like less than 100 bits or so in order to represent 5000 characters, right? So the point I am trying to make is that the absolute optimal encoding depends on the document itself. What we are talking about here is independent of the actual content, right? Even if I don't know exactly what it is that I am trying to convey, I could, for example, do it always with 160,000 bits using UCS4, 40,000 bits using ASCII, right? But what is the best possible thing that I can do? That depends on the actual content itself. So the question then comes, is this solvable in general, right? Now, trying to encode by actual character frequency is not always a good idea because it ultimately depends on the text. You might have one particular piece of text which is just created to show that yeah, these characters are rare, but I'm going to use them a lot, okay, in which case you would probably do poorly in your encoding. And the fact of the matter is what I just mentioned, right? Trying to find out the frequencies of occurrence of different strings or different subsets of bits and encoding them more efficiently is ultimately what any compression program like zip does, okay? And they are better at it because they are doing it independent of the data. They don't really look at whether it's characters or letters, and as long as the algorithm is standardized, I can take any text document or any other document and run it through the same zip and be sure that when it comes out at the other end, it will translate into the original document because the algorithm is now the same on both sides. So that helps us with the storage problem, right? I can always use zip to reduce the amount of data stored. But there is still the question of what about the in-memory storage requirement? That is to say, if I have a document and I load it and I want to, let's say, compare certain strings or search for certain strings, I still don't want to be using 4 bytes per character, right? And then comes the question, is there a better way of encoding? Do I really need to use UCS4 where I have, right, 4 bytes for every character? And can we find a good halfway point? Okay. So as an example, let's look at, is there a way by which I could use 1 byte for most of the common letters, most of the common alphabets, right? While at the same time saying that others I would group them according to frequency and have some kind of a prefix code, right? This idea of a prefix code is something which comes from Huffman coding and related concepts. What it tells us is that as long as there is some way to distinguish whether a given byte or a piece of information is actually supposed to represent some value or is just a prefix telling me look at the next value before you decide what this means, right? It means that I can now have a so-called variable length encoding. Some alphabets would be encoded with 1 byte, others with 2, others with 3, and still others with 4, okay? And based on that, the Unicode people essentially came up with a kind of encoding, right, where they said that, look, if the very first byte that you have, right, or any byte or any 8-bit combination of bits, right, that you find, if it starts with a 0, treat the remaining 7 bits as an ASCII code essentially, okay? So you go back to the original 7-bit original ASCII interface. What this means is that if the very first bit is a 0, you have 7 free bits to encode 128 characters and you have up to 7f, that is 127 characters can be represented. All 0 is treated as a special case, it's the null byte, okay? So obviously what that means is that if the first bit is a 1, I need to treat this differently, okay? So now let's look at first bit being 1. Now I need another condition, okay? The remaining part, does it start with 1 0 or with 1 1 or with something else, okay? So I start setting up different prefixes. If it starts with a 1 0, I interpret it like this, what is shown over here. If it starts with 1 1 0, I interpret it as shown in the 3rd row. 1 1 1 0, interpret as shown in the 4th row, okay? So each of these essentially gives us different combinations. In other words, if I start with 1 1 0, right, then the remaining 5 bits over here and some bits of the second byte. The second byte also I need to be careful, right? I can't just take all the 8 bits over here. Maybe I could have, because I mean, I'm after all saying that I've already decided based on the first byte that this is what it is. But think about what happens if you were just scanning through a set of bytes and you arbitrarily picked on one somewhere in the middle. Okay, you don't know if it's the first byte or the second byte, third byte, fourth byte of a given character. So at any point I should be able to look at the first couple of bits and say, is this special or not? So what that says is, if the first 2 bits in any byte, right, are 1 0, it means it cannot be the first byte of a character, right? If the first bit is a 0, then it straight away means it's a simple ASCII code. If the first 2 bits are 1 1, it means that it is the first byte of a new character. After that we can basically say, okay, if I have 1 0 1 0 1 0 and so on, all of these are just to indicate that these are not the first byte of a character, they are something else. Okay, which means that the X's that are marked over here are all free bits, and I can use them to represent different numbers. And what that tells me is, now I have 5 over here, 6 over here, a total of 11 free bits, which means that I can go up to 2 to the power of 11, 2048 minus 1. So 2047 different Unicode values can be expressed in this way. If I have 3 bytes, then I have 4 free bits here, 6 here, 6 here, a total of 16, which gives me 65,535. And finally I have this, 3 bits, 6, 6, 6, right? Now over here, one further restriction is put. Ideally you have 21, which means that I could have gone up to 2 to the power of 21. But in the case of the Unicode standard, they also put in a further restriction that the first 5 bits essentially have to correspond to the value 10. Okay, why? Partly it's just a question of making it a bit easier to represent and sort of extract the values that are present over there. But you could build something else which actually allowed those bits to be anything. There's no fundamental reason why this has to be restricted. The point is, you have already hit something like 1 million or so different representations, right? So at that point people said, okay, this looks like it's good enough for everything that we need, right? And what's the nice part about it? English language documents, for example, would fit nicely within 8 bits. Other languages, the more common ones, would fit within 16 bits. Less common ones would take longer. Okay, let's take an example, right? This is from the W3 website where it talks about the definitions of characters, and we have these characters. So this is the letter capital A from English, this is something from the Hebrew alphabet, this is something from, I guess, Chinese or Japanese. I can't make out the difference exactly, but the kanji script essentially, right? And what we have is something called a code point, right? So this is something called the Unicode code point 0 plus 0041. Okay, that is a standard. It is always the standard code point as far as this particular alphabet is concerned. This is U plus 05D0, then 597D, and this is 233B4, right? All of these are hexadecimal values. Now this 233B4 tells you that it can't even fit within 16 bits. Okay, let's first look at the UTF-32s corresponding to these. The 0041 corresponds to just this, right? Literally the first 3 bytes are 0 and then 41 hex. The 05D0 gets translated into this, first 2 bytes of zeros followed by 05D0. 597D similarly also gets translated this way, and this other character 233B4 gets translated into 00233B4. So the UTF-32 or UCS4 representation of these code points is very simple. It's basically the code directly converted into a 32-bit hexadecimal number, put zeros in front. UTF-8 is what I just discussed, right? This prefix code that we have over here. And if you go through and you work out what the encoding is supposed to be, you will find that this essentially corresponds, the 41 remains the same, 41, because it starts with an MSB of 0, most significant bit of 0. This 05D0, right, I need to change it, right, because in UTF-8 what will happen is I will need to put in this 110 over here and this 10 over here and use the remaining bits in order to encode what I have. It comes out as D790. Okay, once you put in those values, you will find that this is what it translates to. This 597D instead translates into a 3-byte character. Okay, and this other one, which was already 3 bytes even in UTF-32, translates into a 4-byte representation. Okay, so UTF-8 in other words has all of these possibilities, 1, 2, 3 or 4 bytes in order to represent a single character. UTF-16 uses 2 bytes for most of them and 4 bytes for one of them. Okay, so as you can see, both of these UTF-8 and UTF-16 are variable length encodings. Different characters will have different number of bits required to represent them. The advantage obviously is you hopefully will get a smaller representation in the majority of cases, right. The disadvantage is you now need to sort of look at each character and interpret it based on what its most significant bit and other bits are. Okay, UTF-32 is easy to sort of interpret. I just take 4 bytes at a time and figure out what it means, but it obviously occupies a lot more space. So UTF-8, right, UTF stands for the Unicode transformation format, and UTF-8 is something that uses 8 bits for the most common character set, that is ASCII, which means that all ASCII documents are automatically UTF-8 compatible. Okay, all other characters can also be encoded based on this prefix encoding that we just talked about. Okay, now keep in mind that this particular prefix encoding is not something that you need to know, right. You just need to be aware of the fact that there is a prefix encoding. The exact prefix encoding is determined by the UTF-8 standard and is pretty much implemented by some text processing utilities inside, which automatically know how to scan through a sequence of bytes and interpret them, right. Now obviously, like I said, this means that it is more difficult for text processors. It has to check a prefix, then it essentially is sort of doing a linked list traversal, right, to find out, okay, where is the end of this particular word and what does it mean, right. It's the most common encoding in use today. Now having said all of this, we can come to the question of why is this important or useful to a person developing a web app, right. You need to keep in mind that your viewership, the people using your app, might be coming from anywhere, right. So if they are based in the US, yeah, they will typically just be using regular computers that understand ASCII, all well and good. So if you just stick to ASCII, fine. But in India, for example, we'll find that not just English, computers could have been set up even in the local language, right. So there might be something where even the menus and other things are set up to display in Hindi or in Tamil. In such a case, the browser by itself might be expecting Tamil or Hindi as the first language that it's going to see, and you need to have text processing capabilities internally which can handle any of these characters. And by basically saying that you are going to be using UTF-8 as the encoding for your document, it at least makes it a bit easier for the browser to say, okay, look, this is at least a standard. I know how to interpret the text or the set of bytes that are coming in from the network for this document, right, and that I will then use whatever the built-in libraries that are available for things like scanning through text, for parsing text, for splitting it up into tokens, for displaying it in different ways, figuring out which is a special character versus a alphabet. All of those things will be done based on the UTF-8 encoding. And what you will see is that pretty much most websites today have one sort of a meta tag in them which mentions that the character set being used is UTF-8, right. Now it's common enough that you should probably just say, okay, this should be the standard, why do I even need to specify it? But it's good practice in general to specify it, because there are cases where people may not follow UTF-8, right. Why would they do that? That's not very clear. There might be a case where they have a very limited audience and they find that spending 4 bytes per character, maybe you're in China and you don't want to spend 4 bytes per character because 99% of your audience is going to be using the regular Chinese character set. So you use a more efficient encoding there, right? But UTF-8 is the most common one worldwide at least. And even for us in India, this makes sense because for most practical purposes, it means the maximum compatibility across different languages.